Hi, thank you very much. So I'm Karen Jex. I'm a Senior Solutions Architect at Crunchy Data, and I'm really happy to be here at my first ever Euruko and my first time in Sarajevo, so fantastic. And I'm going to talk to you about how to optimize your database for analytics. This is even better than a TLDR. This is a link to the slides from a previous version of this talk, so it's not identical, but almost the same. So if you don't even want to listen to me talk, you can just go to that link there. First of all, whenever I'm talking at a developer conference, I have to get the confession out of the way. I'm not a developer. I'm really sorry. But as you can see from this diagram of my career so far, I do know about databases. So I was a database administrator for about 20 years before I was a database consultant and now a senior solutions architect, but I still work exclusively with databases. I've worked with a lot of developers along the way, and I've learned lots from the developers that I've worked with, and I really like to be able to give back some of what I know about databases. So what am I actually going to talk about today and why? To answer that question, I'm going to do a quick recap of some of the different types of database activity. You've probably got an application or many applications with a database backend, and that database backend is probably constantly being queried, updated, inserted into by your application connections. So it could be a traditional payroll app, it could be a banking system, an online commerce system, or one of all sorts of different applications. This type of activity is usually called OLTP, or online transaction processing, or sometimes just your operational database activity. And it's characterized by multiple concurrent users, usually performing lots of short queries, and they'll often be doing multiple selects, inserts, and updates within a single transaction. And it's at this point, actually, that I need to apologize for my view of the world. So I see the database and then everything else that goes on outside the database. So you'll see the users connected to the database conveniently ignoring all of that application layer. So just imagine that that's there in between. So most of these applications will constantly be generating data in your database. And that's going to gradually build up. And at some point, the business wants to get value from that data. It wants to glean insights from that data. And for that, you're going to need to run analytics queries. So this analytics activity can take various different forms, and it's got lots of different names. You might hear it called OLAP, Online Analytical Processing, Reporting, Decision Support, DS, Business Intelligence, BI. But it's basically any queries, any activities that serve to answer real-world business questions, such as how successful was this marketing campaign, or what would be the impact on our carbon emissions of performing this action over this one. And this type of activity is characterized by complex queries, often performing joins on multiple tables, working on large data sets. So typically, it's going to be using a lot of resources. It's going to be using potentially a lot of CPU, memory, and I/O. Once upon a time, we had the OLTP databases, and we had the analytics databases, and the two were very much separate. Data would somehow be extracted from your OLTP database and loaded into the OLAP systems, which is sometimes known as your data warehouse, your data lake. And often that was done by a nightly batch or even a weekly batch. That does sometimes still happen, and there are very good reasons for that still happening that way sometimes. But often, businesses want to get insights from the data instantly. They want it in real time directly from the OLTP system. And where you've got the OLTP and the OLAP activity cohabiting, you'll often hear that described as a mixed or hybrid workload. It's not a new idea. Gartner came up with the term HTAP, Hybrid Transaction Analytical Processing, back in 2010, and it's been described in other places as translytical or hybrid operation and analytical processing. So what's the problem with this? It's well established in academic circles that this type of workload presents unique performance challenges. There are papers from back in 2010, 2011, where the researchers identified and discussed the fact that running mixed workloads causes performance issues. And there are ongoing discussions about this and things like what kind of benchmarks can be used to monitor this type of activity. But you'll probably be pleased to hear that I'm not planning an academic discussion. I'd rather focus on what you can do if you're in this situation. How can you make sure that you run performance analytics with minimal impact on your operational database activity? So to recap, your database is probably optimized for your day-to-day OLTP application activity. Adding analytics activity into the mix, so complex, long-running queries that consume lots of resource, means you can end up with the worst of both worlds. You can have analytics queries that are inefficient, but that also slow down your existing application. So now that we've identified what the problem is that we're trying to solve, I set up an environment where I can test things out as we start to look at ways to fix those issues. I'm using Postgres for this because it's the RDBMS that I know and love and the one that I work with on a day-to-day basis. And also it's quick and easy to set up and work with. It was very heartening to hear the Postgres for everything from Euruko just now. And in particular, I'm using pgbench, which is a simple benchmarking tool that's available by default with Postgres. So, first of all, we create and populate the pgbench tables by running pgbench with the -i, the initialize flag. In this case, I'm doing it in a database that I created called Euruko. And I've asked it to give me a scale factor, -s, of 100, just so that I've got some kind of size to my tables. I've also asked it to create foreign keys between the tables so that it simulates somewhat an OLTP type database. You see it shows us the progress towards generating 10 million rows of test data, and it takes about 25 seconds. And this is what it creates for us. It creates 4 tables: pgbench branches, accounts, tellers, and history. The number of rows listed here is what you'd get if you left scale factor at the default of 1. So because I set it to 100, I ended up with 10 million rows in the pgbench accounts table. The pgbench history table will start off with 0 rows at the beginning of each pgbench run, and they'll be inserted as you go along. And I've included a link to the documentation there just in case anybody wants to look up how that works. By default, pgbench simulates OLTP activity by repeatedly running this transaction. It's loosely based on the TPCB benchmark. Each transaction is made up of several SQL statements. So you can see there are 3 updates, a select and an insert. And each one will take random values of AID, TID, BID, and delta. You can pass in any scripts you want if you want it to simulate other kinds of activity. So then when you want to actually simulate some activity on the database, you run pgbench without the -i flag. You tell it how many concurrent clients you want. So in this case, I've used -c10 for 10 concurrent clients. And how many seconds -t you want it to run for. So here I ran it for 1200 seconds or 20 minutes. The output that you get will show you things like how many transactions were processed, what the connection time and latency were, and what TPS throughput you got. So in this case, I got about 5,000 TPS. This is just running on my MacBook. So the goal of this isn't to try and get the best possible throughput, it's just to give you an idea of what you might see. Okay, so we've got a demo environment with some tables and some data in it. Then I mocked up an annual sales report type analytics query against that PG Bench history table. It manipulates the data in the M-time column to get something that looks like year and month. It groups and orders by year and month, and it calculates some totals. So you'll probably notice that as analytics queries go, this one is extremely simple, but it's good enough for demo purposes. And this is what the output looks like against those 10 million rows that were inserted into my PG Bench history table. Okay, so if we want to have a look at the execution plan for that query, so we can see what it's doing behind the scenes, we can use Postgres's explain analyze command. I connect to my database via PSQL, I type explain analyze, and then my query. So the analyze keyword here tells it to actually run the query. So you'll get real stats rather than an estimation of what it's going to do. So wait for that to complete. In this case, we can see that it took about 6 seconds, just under 6 seconds, to run our analytics query. It's doing a sequential scan on the PG Bench history table, so it's reading the entire PG Bench history table. And we can see we've got a sort method external merge disk. So it's actually writing some temporary files to disk and doing the sorts there. Just in comparison, the select statement in the PG Bench transaction that we looked at takes about a millisecond. Okay, so we've got the environment in place. Let's have a look at some of the techniques that you can use to optimize analytics activity without slowing down your application. It's not going to be an exhaustive list, so the idea really is to give you enough to get started. And again, I'm using Postgres for the details, but the ideas are applicable to other RDBMS. Okay, so configuration parameters. As I said, your database configuration parameters are probably, or at least hopefully, optimized for your day-to-day operational database activity. If not, I highly recommend going to have a look at them. And that gives me the perfect excuse for a shameless plug, because this is a link to a talk that I gave on exactly that subject at DjangoCon EU last year. Okay. Some configuration parameters need to be set across the entire Postgres instance. For those, you're going to have to find some kind of compromise to find the values that work best for your hybrid workload. But other parameters can be set for specific users, so you can set them to different values for your application users and for your analytics users, and some can even be set for individual sessions or queries. I'm just going to walk through a few of the different parameters, and I'm going to encourage you to test things out, to read the documentation, and also take note of the comments in the Postgres default configuration file, because they're actually quite useful. First of all, database connections, and this is something that Euruko referred to in his talk as well. The chances are you won't have too many concurrent analytics connections, but those connections are likely to be using a lot of resource, so you probably want to make sure there aren't too many of them. The max connections parameter is set for the entire database instance. That tells you the maximum number of concurrent connections that are allowed to the entire Postgres instance. The default is 100 on most systems, and you probably don't want it much higher than that. Definitely no more than a few hundred if you can help it. And you probably want to limit the number of analytics connections to much less than that. And to do that, you might want to look at connection pooling, so for example, PG Bouncer, so that you could create a separate, smaller pool for those analytics connections. Workmem is the maximum amount of memory that can be used by a query operation before it spills to disk and creates a temporary file. So we saw those temporary files created in the execution plan for our query. By default, it's 4 megabytes. But if you've got queries that are performing complex sorts or hash operations, they might need a bigger value and sometimes a much bigger value. You can check if workmem potentially needs to be increased by setting log temp files. If you set that to 0, it will log in your Postgres logs every time one of these temporary files is created, so you can see that you're spilling to disk and potentially need more workmem. Just watch out, because if you've got multiple concurrent users and you've got lots of these complicated queries, each of those could actually be using many times workmem, so you can very, very quickly use up a lot of memory. So to avoid using too much, you're probably better to set it to a high value just for certain queries or certain sessions that really need it, rather than across the whole instance. I tested out the analytics query that I created with different values of workmem. So we already saw with the default value of 4 meg, it was taking around 6 seconds, and it was doing that sequential scan and those disk sorts. So it was creating the files on disk. Here I changed it to 100 megabytes to see what that did, and regenerated the execution plan. Just taking a minute to do that. I might not wait for it to do that, but it took still nearly 6 seconds, and it still did an external disk sort. So setting it to a large value doesn't always help all that much, but it's very much use case dependent. In the interest of time, I'll just move on from there. And I even tried increasing it right up to 1 gigabyte to see what happened. That got rid of the disk sort, so we can now see a quite large in-memory sort, and it took the time down to about 4.5 seconds, but that to me doesn't seem like a fantastic trade-off for the sake of using a gigabyte of memory just for that one small analytics query. Obviously, again, it will vary from case to case, so try out different values and see what impact it has on your queries. If you're concerned that certain queries might run for too long, you can set statement timeout. So that will abort any statements that run for longer than the specified amount of time. By default, it's set to 0, which is disabled. But you can set it either for the whole instance or just for specific sessions. So it probably makes sense to set it to an appropriate value for your analytics sessions. So for example, your analytics queries, some of them, it might be okay if they run for many minutes or even longer, but you might want your application statements to not run for longer than a certain number of milliseconds. So as I said, statement timeout by default is set to 0, which is disabled. I set it here to 2000 milliseconds or 2 seconds. And then I tried again to run my analytics query just to see what effect that has and check that it's working as expected. So now I can see that it doesn't get to finish. I get the error cancelling statement due to statement timeout after just over 2 seconds. If you want to make sure that any statement that gets timed out in this way is logged, so you know that it's happening, make sure that log min error statement is set to error or lower. So you can see all the different valid values here, from the least severe, debug 5, up to the most severe, which is panic. So if you set it to error, then error, log, fatal, and panic messages will all be written to your Postgres logs. Indexing strategy. You'll probably need to create specific indexes for your analytics queries. But obviously bear in mind that indexes have to be maintained, so they will have some impact on your operational activity. So if you create too many indexes on your application tables, that can start to slow down your inserts and updates. So you, again, need to get some kind of balance there. As well as creating indexes on one or more table columns, you can also create indexes on functions or scalar expressions computed from your table columns. So our analytics query, for example, contains expressions to calculate something that looks like year and month from the mtime column. If we created an index on the mtime column, then the query planner wouldn't be able to use it for that particular query. So what we can do instead is that we can create an index on the expressions that are used in the query. So in this case, 2000 plus hour and modulo 12 of minutes. So that takes longer to create than it would if I just created it on the index, because it's got to do those calculations as it goes along. If we then analyze our query again, then we should see that it's actually using that index that we created. Okay, so we can see that it's doing index scan using that index that we just created. Takes the query time down to just over 4 seconds in this case, and we don't have any of those disk sorts. Obviously, in this case, we're selecting all of the data, so potentially using an index doesn't help as much as it could, case-by-case basis, and just be aware that it will have an impact on your operational activity, so you need to benchmark that to see if it's acceptable. Most analytics queries aggregate, sort, and calculate large amounts of data. So they do totals, averages, comparisons, groupings, etc. And these obviously are resource-intensive operations. So it can be useful to pre-calculate some of that data. So pre-calculate, pre-sort, pre-aggregate, to make those queries less expensive at runtime. If we create columns in a table with the generated always as keyword, then the column value will be automatically calculated based on the expression. So in this case on the slide, the sum of columns A and B. The stored keyword says that it should be actually physically stored in the table rather than just calculated at query time. So in that select, you can see that C has been calculated automatically. Again, it will have some impact on inserts into that table, so you need to benchmark that and see whether that's an acceptable trade-off. So in our case, we can add year and month columns to our PG Bench history table, telling Postgres to generate the value automatically using the definitions that we've got in our reporting query. Now, in this case, it's going to take a while because I've already got those 10 million rows in the table, so it's got to calculate those values and insert them into those columns. So now, once that's in, we can use those calculated columns in our query instead of actually putting the expressions, so I can just select year and month. So that takes the query time down to just over 3 seconds. Sorry, I should have left that to wait for longer. A materialized view is a physical copy of the results of a query that can be queried just like a normal table. Materialized views are useful for pre-aggregating data, and they're particularly useful if you don't need completely up-to-date data. If, for example, data from 10 minutes ago, an hour ago, even a day ago is acceptable, you choose how often you want to refresh that materialized view to keep the data fresh enough for your reporting purposes. And you can also create indexes on materialized views to make them even more performant. So to create a materialized view that stores the results of our analytics queries, we can use create materialized view as, and then use our select statement. And then we can just select year, month, and total sales from the materialized view instead of running the analytics query. So this takes it down to a couple of milliseconds because it's only having to select from that 14-row materialized view instead of from the entire table. In the real world, our analytics query is probably just one small building block that's potentially used in many different reporting queries. So you could rewrite all of those reporting queries to select from the materialized view instead of from that base table. And of course, the best way to Improve performance of something is usually by not doing it. So if you can, don't run analytics queries on your main database at all. Even if you don't have a completely separate analytics environment, there are probably some things that you can do. Most database environments already have a high availability architecture in place. So that means you've probably got one or more standby databases that's replicating from your primary. So it's kept in sync with your primary and available for read-only transactions. So you could send your analytics workload to one of those to take the load off your primary database. Just be aware that physical replication gives you an exact copy of your primary database. You can't create separate users, you can't create indexes, you can't change the layout of the schema or anything like that. Any changes that you need for your analytic workload would need to be made on your primary database and replicated across. So another option would be to use logical replication. You can use that to replicate just certain objects, so just certain schemas or tables from a publisher database to a subscriber database. And since Postgres 16, which came out in 2023, you can do logical replication from a standby, which takes additional pressure off your primary database. Logical replication is much more complicated to set up and maintain than physical replication, but it does give you a lot of flexibility. You can replicate just a selection of objects. You can replicate to and from multiple targets and sources. Your subscriber database, so your replicated database, is available for read-write. So you can create indexes, users, materialized views, or anything else that you need just on that subscriber database. So in summary, we've looked at various different techniques that you can use to make sure your database is optimized for analytics without slowing down your application, or at least only slowing it down an acceptable amount. If you can, use physical or logical replication to create a separate database for your analytics workload. Tune your configuration parameters so that they are a good compromise for your hybrid workload. Consider your indexing strategies. Create generated columns or materialized views so that you pre-aggregate and pre-calculate data. And don't forget that you can combine all of those techniques. You can create indexes on your materialized views. You can change your configuration parameters and do all of these other things. Thank you so much. This is a link again to that previous version of the slides. I'm in the process of creating an annotated version which will be available on my blog. And I need to do a quick congratulations to Erat and Yuri, who have won a signed copy of Andrew Atkinson's book. So come and see me afterwards and I will hand that over to you. Thank you very much.